This video is brought to you by Munro Associates.
From new product development to teardown benchmarking, Munro offers comprehensive solutions. We specialize in reducing costs and weight, drawing from 35 years of experience to help you maximize profitability and elevate your projects. Contact Munro Associates today, and let's turn your next project into a success story. Munro, innovation starts here.
Hey boys and girls, we're right here in front of Archer, our next, if you like, vertical takeoff machine company. As you know, I am kind of into going up, and I really am looking forward to getting a tour here. And so let's go in and have a look. And here we go. So
Hey,
Tom,
Sandy.
thank you very much for the invitation, and we're just looking at midnight right above us here.
Yeah,
Yes.
welcome to Archer.
Well, thank you so much. Why don't you give us a little background on you before we get going?
Yeah, absolutely. So my name's Tom Muniz. I'm the CTO here at Archer. I've spent most of my career working on eVTOL aircraft, which is kind of a funny thing to say, but
Yeah.
it's true. My job here at Archer is kind of running the technical teams that are working on building these electric aircraft we're working to bring to market here over the next couple of years.
Cool. And as my viewership knows, I'm very, very much into vertical takeoff. I really think that this is the wave of the future. I mean, yes, Tesla makes great cars, and so do a lot of other EV companies, but at the end of the day, roads and highways cost a lot of money.
Yeah.
A little cement pad, an apron, doesn't cost a heck of a lot of cash. So I'm really looking forward to the days when we can save a lot of money on concrete.
Yeah.
And basically put it into aircraft like this one here.
Yeah.
So I'm all excited.
It's a super exciting time,
Yeah.
I would say, in the industry, because we're now at a point where we can leverage a lot of the investments that have gone in, to particularly the auto industry, electric automobiles, to make these new types of aircraft that can
Yeah.
take off and land vertically like a helicopter, but fly forward like an airplane really efficiently, really quietly. Basically, all the benefits that helicopters provide as far as
Yeah.
vertical lift, but without a lot of the downsides, noise pollution, cost, safety, etc.
Yeah.
So yeah, really excited to have you here. We're going to show you a bunch of our manufacturing facilities where we
Great.
produce batteries, electric motors, where we do some of our system integration. So yeah, a lot of cool stuff to show you.
Yeah, before everybody gets all excited, right? You're going to show us your battery pack,
Yeah.
not the cells. Yeah.
Well, we'll show you how we take cells and turn them into
Yeah,
battery
battery
packs.
packs. Yes. Okay. Good. So where do we start?
Well, we're going to head down the road to our lab just one block away. So Sandy, this is Heath Smoot, our head of
Heath.
NPI manufacturing.
Nice to meet you,
Nice to
Sandy.
meet you. Nice to meet you, Heath. Yeah.
So we're here in our electric engine R&D assembly lab. So this is where Heath and his team are figuring out the process that will ultimately scale up when we take our engines into production here
Wow.
over the next year.
Wow. Cool. I'm very impressed. We don't see too many little gearboxes that look like that in the auto industry, and I'm really impressed by the motors, the motor casings. This can't be a casting.
No, it's definitely an aluminum forging, a 7000 series material for the aluminum forging. We do that to increase the strength of the material so we can
Yeah.
get the thinner wall thicknesses and the lightweight out of the material.
Yeah, that's that is one of the things that basically differentiates aircraft from automobiles. Weight is a big deal with automobiles, but it's mandatory for anything. Like at Boeing, it was $600 to $1,000 a pound. If you could get rid of a pound, they'd be happy to pay $1,000. So
Absolutely.
I don't
we
think I
count
could-
every gram.
yeah,
Every
yeah,
gram.
that's right. Actually, that's one of the things I said in BYD when I was teaching them how to design. Yeah, 1 gram every day, every engineer. Sounds fine, right? Until you've gotten maybe through 1 kilogram, and then all of a sudden everybody's scratching their heads to try and figure things out.
That's right.
But this looks
Every
brilliant.
part you see here, even like the rotors, right? Hubs,
Yeah,
very
yeah.
thin hubs, and a lot more magnets, right? So you got more mass on the magnets, but lighter weight hubs.
Yeah.
We need that more torque.
Yeah. Wow.
But
So-
you'll see very common with the automotive industry still though. So from a process perspective, we're not like going out there and making, other than our newer rotor, which we can go over and look at some of those processes there. But otherwise it's very normal production type processes. Like, just looking at the gearbox assemblies there,
Yeah.
right? With your ring gears and then your pinion gears.
Yeah.
It is a very common automotive. So we're
Yeah.
not really taking this step where it couldn't be approved, and we got process history across multiple different
Right.
companies. We got a good supply chain.
Yeah.
All those things are helpful for us to get to market early.
So the assembly here is basically integrated inverter with electromagnetics with the gear reduction, the planetary gear reduction.
Yeah.
So the idea is this gives us the self-contained unit,
Yeah.
and we have 12 of those on the aircraft that each spin their own propeller.
Another thing we've developed in-house, just because we're a little bit more novel than like automotive.
Yeah.
And sorry, it's a little louder in here.
Yeah. No problem.
And you can see like this unit is all thermocoupled up. So we're doing all of
Right.
our testing, collecting our data. The biggest differences within these dynos that we've developed here is typically you have a massive AC motor on the backside, a drivetrain directly into there. The reason we didn't go that way is because it does take a massive motor, and to put this many dynos in, our testing is 6 hours for every motor. So you got to cycle these things a long time. So we really are using our own motors to do the regen side and the torquing.
Oh, cool.
And then that's how we're driving and testing our other one. And then we can flip flop and do them the opposite way. So we can run this thing
Yeah.
for 12 hours, test 2 engines, and not have to change over at all.
Yeah.
And these test stands will go through all variations, right? So the fixtures change over and you can couple up all the different systems. The other major difference here is this goes full tilt mechanism through the flight. So this whole table is on a rotary. And as you go through your flight cycles and sequences here, the whole table and the drive system rotate as if it was on the aircraft tilting. That allows us to manage our cooling systems, understand like the oil flow. As you tilt the oil, obviously you got less than other areas. You need to make sure the pumps pick up and move it. And then we got a heat exchanger here. So we can also test our heat exchanger. We can control the oil temperature, or we also have a fan system that acts just like the propeller blades that do the cooling. So we can either control all the oil ourselves, do other testing, or we can control it based on exactly like flight. So these are all about just collecting data, right?
got it.
Pulling the data, understanding what we have.
Yeah. I love it. Yeah. I don't think I've ever seen anybody use the trunnion design for the inversions and stuff like that.
I would agree.
Yeah. Oh, that's cool. So did you design your own machines as well?
Yes, yeah,
Oh.
we did these. Yeah, this is
Maverick.
Yeah, we got to play too, right?
Oh, wow, yeah.
We named them all.
Yeah. Really?
It is a pretty cool capability, though, that the team, developed and actually
Yeah,
built
yeah.
all of the test equipment in addition to the.
No,
the
I love
systems.
the idea. I mean, this is the old Ford way. We're going to develop an engine. Oh, we're going to develop our own machine tools. Oh, we're going to develop our own assembly systems. We're going to develop our own testing and validation and whatnot. And that way, you really, really, and truly understand everything that has to do with the product. Tragically, I don't want to do it again, but everybody's already heard me throw rocks at the idea of, wow, we can make an extra 50 cents if we just outsource this. And when you outsource it, you outsource all your intelligence. Your profound knowledge is gone, and you can't get it back. Because once you give it to somebody else, guess what? They're selling it to everybody on the planet. Oh, but we're saving 50 cents, and we'll keep that up for maybe 2 months. Yeah, good idea.
The great
This is
thing
good.
about developing these ourselves is we were able to design these and assemble them in, I think it was like 6 or 8 months. Yep. And they cost, like a couple $100,000 each, as opposed to if we were going to send that out, it's like an 18-month, $1 million a piece kind of a job.
Yeah.
So.
Yeah, and then you can control all the
Brilliant.
data you get. You know what you have, to your point,
Exactly.
right? You understand it all.
Right.
And we can, change within it, right?
Yeah.
Get more and more data.
So Sandy, this is Isaac Harper.
Nice to meet you.
It's our
Isaac,
powertrain
nice meeting you.
manufacturing.
Yeah, yeah,
So we're here in our battery pilot line.
yeah,
It's a little bit different than the motor lab you came from.
yeah.
Here we've taken the next step to take the processes that Isaac and his team have developed and put them into more of a proper pilot line, if you will.
Yeah.
So Isaac's going to talk us through what we do in the,
All right,
in the
perfect.
shop.
So as far as the product design goes, there are 6 battery packs per aircraft, 3 mounted from underneath in each wing. Each battery pack is about 24.5 kilowatt hours. We use, this is a dummy cell, completely
Yeah.
safe.
Right, yeah.
We use a 2170 cell from Molicel. It's a 210 S7P configuration. We have our high voltage cables, our auxiliary cables, low voltage communication, then our interfaces to the aircraft, and then our coolant circuit, inlet and outlet. So there's 6 of these per battery, or per aircraft. Okay.
And the
that's
reason
quite
there's 6 is because we don't want to have any single points of failure
Yeah.
in the aircraft. So just like with the engines, we can lose any engine and still fly safely. We can lose any battery pack, still fly safely. The next level architecture down is that 2 battery packs are paired on a single high voltage bus. And there's 3 of those per airplane, if that makes sense. So it's all about redundancy, kind of same way you would design systems in an airliner.
All right, so we'll take a look at how we build the pack over here.
Great.
All right, so a lot of this is adopted from the automotive industry.
Yeah.
So we have cells that arrive, take the boxes of cells that arrive from Molicel, we scan the QR code of the box. We've completed our cell test and load operations for today, so we're just running in kind of a demo mode right now. But essentially the box of cells goes into the machine. 7 cells are picked up at a time from the machine. They're then loaded to this dial table. Before we place the cells onto the dial table, there's a Keyence camera that takes an image of the bottom of the cell. For every cell that we take, we take 3 sets of pictures. So a bottom picture, a top picture, and then at this station over here, we're spinning the cells. So we're essentially unwrapping and taking an image and unwrapping that. So we're looking for any damage that may be present, like dents or scratches or electrolyte salts.
Yeah.
From here, we read the individual QR codes on the cells themselves. The next station is an electrical test. So a set of electrical contacts come down. We measure open circuit voltage, ACIR resistance, and cell can temperature. From here, this station here is a Keyence sensor that essentially is measuring the cylindricity of the cell. Later on, we're inserting the cells into our foam cell holder, and that's a relatively tight slip fit. And so we took experiences when building manually and felt a little bit of friction during occasionally when inserting. So we were hyper aware that we could have potential issues when inserting the cells into the pack. So we, at this point in our development, we're measuring the cylindricity of every cell. There's another camera up here. There's reject drawers. So if a cell were to fail, it would come back to this point. The Scara robot would pick up the cells and place into a password protected reject drawer. So this is the test portion.
Yeah.
And then this is the load section of the line. So we load up a cell holder on the back half of the line. It goes in. We have a 2D displacement sensor here that's measuring the individual bore holes on the cell holder. So we can create an offset map for X, Y, and theta. That then informs where the robot should go and place cells into the pack. This machine can populate an entire pack in 20 minutes, or 3 jobs per hour. From here, the next section of the line is where we dispense adhesives. So kind of where we're at in the development here at Archer is, this is our pilot line. We've only automated where it relates to the quality of the product. Examples would be adhesive dispensing. You need to robotically dispense that to control bond line thickness or percent coverage. Or where it relates to the data collection. So here over at the cell test and load, we collect over 10,000 pieces of information per pack. So from a traceability perspective, we needed to automate. And then there's one example where we've automated to eliminate the arc flash hazard for the operator. All right, so over here, what we haven't done is to automate for manufacturing efficiency or cost at this point. That'll be the next phase. So here, this is a multi-purpose cleaning station. So it's a single piece of automation, so a gantry robot that has both vacuum cleaning to remove any debris that might be on the pack, or plasma cleaning. So there's a plasma nozzle there. That's to prepare the carbon fiber surfaces.
Blading, yeah.
Yep, exactly. So we clean the pack, then the pack transfers over to this station. This is a multi-purpose dispense station. So we're running trials in advance of doing some thermal interface material dispensing later tonight. So this station, we dispense the thermal interface material, which connects the cells to the cold plate or the heat exchanger, or we also use the same station to dispense the gasket material that connects the carbon fiber enclosure to the hex itself. This is kind of a marriage station where we, using a lift assist, we can pick up the heat exchanger, place it onto the pack. So imagine that there's a sandwich, the pack is a sandwich. It then goes into an elevator up and into a curing tower. So that curing tower would clamp the heat exchanger together, wetting out the surfaces. In that station, we're recording the pressure, the temperatures, the ambient humidity, all being sent to our MES. From here, we've actually built the pack upside down at this point. So the pack comes to this station, we pick up the pack, we flip it over so the cell terminals are facing the ceiling. So this is for laser cleaning. So we're cleaning the top surfaces of the cells where we will later weld to. So again, very similar to what you'd find in an automotive factory. Large granite machine base for vibration dampening, gantry system, coherent laser power source and optics, a set of cameras and laser sensors to identify where the part is relative to the pack. So we can clean all of the surfaces, so roughly 4,500 welding locations, and again, roughly 20 minutes. So the 3 jobs per hour operating at 3 shifts per day has the automation, or the automated stations has the capacity to build roughly 15,000 packs per year. Obviously, there would be some bottlenecks that we have to break. Those bottlenecks are relatively inexpensive, like the curing towers. So in its current state, we can build 1,000 packs per day, but with the high value equipment like the cell test and load, or the potting stations, or the laser stations, those have the capability to build 15,000 packs per year.
Currently 1,000 packs per year out of this facility. But if we essentially deal with those bottlenecks, essentially like this equipment is all set up to do that 15,000 packs per year, which supports us building, beyond 650 aircraft per year, just with what investment we've already made. So, we're quite far along in far as maturing these processes.
So what do you think you ultimately would get to? Because we talked about the paradigm, and like I said, we had thousands of orders when we showed it and whatnot, and we were thinking, hey, you know what? We might be able to sell 60,000 of these a year, because what we were looking at was Indonesia. Thousands of islands that got people on them that have no way, except for some kind of an outboard motor. Any kind of real speed travel is impossible. You guys, your market must be 1,000 times that.
Yeah, we're definitely real believers that there's a huge market here. The factory that we're opening in Georgia will have the capacity to produce up to 650 aircraft per year in its first phase. We could expand on that same site to ultimately produce, we think, about 2,000, maybe a little more than 2,000 airplanes per year. Beyond those kind of numbers, though, there's a lot of other things that we'll need to think about differently, in particular the composite structure. So, we're not seeing that in any of our facilities today. But if we start talking about building, tens of thousands of composite primary structure pieces per year, we would take different design approaches for that structure. We would take different manufacturing approaches, moving away from, pre-preg carbon fiber to other processes, RTM, different material systems.
Well,
faster.
RTM isn't your friend either. I think that right now we're watching all the supercars being made that are made out of carbon fiber, and they're all using sheet molded compound. SMC is so fast. I mean, one stroke clunk, and I got a body, and that's what we were just looking at over at Aptera. You should go down and have a look at what they're cranking out, because you could really make a big difference as far as speed. With a slightly different mode.
I think what it's going to be for us is a lot of tailored manufacturing processes for each part, because some things SMC is going to make total sense. Other things that are needing to still be weight optimized and carry significant loads, like wing spars, those probably make sense with some
that would be it. Yeah.
Some like AFP process, automated fiber placement type process. Yeah. But then the question is, can you get to a resin system that has a faster cure cycle than what we use today, which is like an 8-hour autoclave cycle? Can you bring that down with snap cure resins and those sorts of things? But I don't think it's a one size fits all. I think it's
it's going to be, you're going to have a lot of different processes and whatnot. But I will tell you that really and truly BMW with the i3, they solved a lot of problems.
Yeah.
And we still sell that report. That thing cost me $2 million. I'll never get my money back. But we found out everything and stuck it in there so that anybody that wanted to get into something that was like high volume, and that is a high volume, that's a 50,000 a year kind of a car.
Yeah.
And if they can do it, you could do it. So here we are at the simulator.
Yep. So this is one of our simulators. This is actually the Iron Bird lab is what we call it.
Oh yeah.
So it's basically our most complete simulation environment, where on the other side of the glass here, we have all of the components of the aircraft wired together as they would be in the vehicle. But instead of, servos that are feeling forces generated by, wind going by, they're connected to the loads driven by simulation equipment. Yeah. And so we basically use this lab to put the system hardware and software through its paces, inject failures, find what works and what doesn't work. And we can do that with a pilot in the loop here. This is not intended to be like the high fidelity pilot simulator. We'll see that in the next lab. But this is where we really verify that everything on the aircraft works as it's intended. So, if you look at the kind of main racks here, you can see the avionics boxes mounted as if as they would be in the aircraft.
Yeah.
The kind of lateral wire bundles going out as they would be in the wings to the various components, batteries, motors, actuators, etc. Just like in that other lab, we have the real flight deck hardware. These are like the same side sticks.
Yeah.
But instead of having all of the systems, we just have a subset running on the server racks that you can kind of hear fans running on.
Yeah.
But if you want to go ahead and scoot your chair up, there's a little orange latch you can pull here, and then move yourself forward until you can kind of grab the sticks comfortably.
I can grab the sticks comfortably.
Yep,
I only
that
see
looks
one.
So there's pedals. They're only used for brakes.
Oh, okay.
So you don't really need to use them for anything we're gonna do today. But basically, it's very easy to fly. The idea is you're providing the aircraft very high-level inputs for what you want to do, not having to do like the inner loops of getting the aircraft to kind of hover or stay in place. So if you take your right hand and pull back on the stick, that'll tell the aircraft you want to climb vertically. So whenever you like, you can let go of your right hand.
I think what I'm going to do is get beyond these yellow posts.
Sure. Yeah, a lot of the stuff you see here is set up for our pilots to do handling quality evaluations, flying very specific maneuvers, evaluating ways to control the aircraft.
So can I...
So if you press forward, you can go down.
You press forward, you go down?
So your right hand forward and back is up and down. And if you let go at any point, the aircraft will maintain position and just stay in hover. And so left and right with your right hand, that points the nose. Left and right, just as you did. So if you want to go forward, it's your left hand.
Oh, I see. You got to use.
So if your left hand back goes back, left hand forward goes forward. And so right now the aircraft is in essentially hover mode. And so it'll keep you at 30 knots or below. but the intended operation is you want to take off and then start flying like an airplane.
Yeah. So how
And
do
so if you use your left thumb to hit that hat switch and push it forward, forward instead of down.
oh, sorry, forward.
Yep. So that's
Okay.
going to put you in automated acceleration mode, and this will essentially transition you to forward flight. So if you look at the, graphics for the
yeah.
propellers, now we're accelerating. Those tilts are moving down. You can see,
moving
we're
up.
going 65 knots, coming up on 70 knots, and then it'll essentially put you in airplane kind of mode. And once you're in that mode, essentially the sticks do the same things. So if you want to go faster, you push the left hand forward.
Oh, the left hand forward.
If you want to turn, you go left and right with the right stick. If you want to, climb like in an airplane, pull back on the right stick. It's essentially as if you're flying just any sort of typical airplane. There you go, on the deck.
On the deck, good.
Not bad.
Not bad. I didn't crash. No one died.
Success.
Grace isn't laughing yet. Yeah, that's great. I'll tell you, this has been a great tour. Thank you so much, Tom. I mean it
Thanks,
sincerely.
Andy.
This was great. I really love watching anything that is coming together in a right and good way, like this thing is. So thanks again, and thank you for watching Munro Live. Thank you.